Welcome back. This video is a complete guide to greedy algorithms in Python, one of the most powerful and elegant problem-solving paradigms in computer science. We'll develop the intuition for when greedy works, prove it rigorously, apply it to 10 classic problems, and understand exactly where and why it fails. Let's dive in. Next, a greedy algorithm makes the locally optimal choice at every step, hoping that a sequence of locally optimal decisions leads to a globally optimal solution. There's no backtracking, no trying alternatives. Just one committed choice at each step. Beat. For greedy to be correct, two properties must hold simultaneously. The greedy choice property. There always exists a globally optimal solution that includes the greedy choice. You don't miss the global optimum by picking locally. And optimal substructure. An optimal solution to the full problem contains optimal solutions to its subproblems, the same structural requirement that makes dynamic programming work. Beat. The coin change example cuts straight to the heart of when greedy works and when it doesn't. With standard US coin denominations, 25, 10, 5, 1, greedy always picks the largest coin that fits. For 41 cents, grab a 25, then a 10, then a 5, then a 1 to 4 coins total, which is optimal. But change the denominations to 10, 6, 1, and ask for 12 cents. Greedy grabs the 10, seems sensible, then needs 2 ones. 3 coins. The optimal solution is 2 6s, just 2 coins. Greedy picked the wrong local choice and got stuck. The greedy choice property fails here, because grabbing the 10 destroys the ability to reach the global optimum. Beat click. The decision diagram says it cleanly. If your problem has both the greedy choice property and optimal substructure, greedy is the right tool, on log n, or better, simple, elegant. If either property is missing, you need dynamic programming or backtracking. Beat click. Compared to other paradigms, greedy explores just one path through the decision space, always the locally best one. Divide and conquer splits the problem and recurses on all halves. DP systematically solves all subproblems. Backtracking explores all valid paths. Greedy is the fastest of these, but it requires a correctness proof to trust. Next, the activity selection problem is the foundational greedy algorithm. Given n activities each with a start time and end time, find the maximum number of non-overlapping activities you can schedule. Click. The greedy insight is elegant and non-obvious. Always pick the activity that finishes earliest. Not the one that starts earliest. Not the shortest one. The one that ends soonest, because it leaves the maximum possible window open for future activities. Beat. Click the algorithm. Sort by end time. Take the first activity. For each subsequent activity, take it only if its start time is at or after the end time of the last selected activity. No overlap. Scan once through the sorted list. 2 data points, the sorted array, and a single last _end variable. For the 11 activity example, we select 4 activities ending at times 4, 7, 11, and 16. Beat. The Gantt chart visualizes the result perfectly. 4 non-overlapping activities in green, 7 rejected in red. Notice that all 7 rejected activities overlap with at least one selected one. The greedy selection finds no gap to exploit. Beat. Click Y is earliest finish provably optimal. The exchange argument. Suppose an optimal solution uses activity X where our greedy algorithm would have chosen activity G, and G finishes earlier than X. Swap X for G in the optimal solution. Since G finishes no later than X, every activity that was compatible with X remains compatible with G. The count stays the same. So the modified solution is equally valid. Therefore greedy is at least as good as any optimal solution. Beat click. The weighted variant, where each activity has a value and you maximize total value, breaks the greedy property immediately. Taking the earliest ending activity can sacrifice a single high-value activity that fills the entire window. Weighted activity selection requires dynamic programming. And the min_meeting_rooms function shows the natural extension, finding the minimum number of conference rooms needed for all meetings, using 2 heaps, one for start times, one for end times, tracking concurrent usage with a counter. The fractional knapsack problem. You have a bag of capacity W and a set of items, each with a value and a weight. You want to maximize total value. Unlike the 0/1 version, here you can take fractions of items, like scooping as much gold dust as fits. Click. The greedy insight is immediate once you allow fractions. Always take the item with the highest value to weight ratio first. If you can take all of it, do so. If not, take as much as the remaining capacity allows. B-click. The algorithm sorts items by ratio in descending order. For items A, value 60, weight 10, ratio 6.0, B 120, ratio 5.0, and C 120/30, ratio 4.0, with capacity 50. Take all of A, 10 kilograms, 60 value. Take all of B 30 kilograms total, 160 value. Remaining capacity, 20 kilogram. Take 2/3 of C, 20 kilograms, 80 more value. Total, 240.0, which is provably optimal. Beat click contrast with 0/1 knapsack on the same items. Without the ability to take fractions, we're limited to whole items within 50 capacity. The DP solution gives 220. You take A plus B or B plus C, but always fall short of the fractional result. Fractional knapsack always gives a result, at or above 0/1 knapsack. Dividing items can only help. Click the comparison table. Fractional knapsack, greedy, ON log N, provably optimal for divisible items. 0/1 knapsack, DP, ON times W, provably optimal for integer items. The fundamental difference is whether you can take partial items. If the problem requires whole or nothing, fractional knapsack is the wrong tool entirely. Huffman coding is a greedy algorithm that builds an optimal lossless compression scheme. Characters that appear frequently get short bit codes. Characters that appear rarely get long ones. The key insight: never waste short codes on rare characters. Click the algorithm works by building a binary tree bottom up. Assign each character a leaf node weighted by its frequency. Then greedily merge. Always combine the two lowest frequency nodes into a parent whose frequency is their sum. Repeat until one root remains. Each left branch is a 0 bit, each right branch is 1. The code for any character is the path from root to its leaf. Beat. Step through the build process. Start with individual character nodes ordered by frequency. Pop the two smallest, say E and F, with combined frequency 3, merge them into an internal node. Push that merge node back. Repeat. The most frequent characters end up closest to the root, earning the shortest codes. Beat click. Look at the resulting tree for A, B, 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 C, 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 D, D, D. B with frequency 7 gets the 2-bit code 00. A with frequency 5 gets the 1-bit code 1. Meanwhile, E and F with frequencies 2 and 1 get 4-bit codes. Compared to fixed 8-bit ASCII codes, Huffman shrinks the encoded string dramatically. The ratio printed confirms the compression, and decoding the bit string perfectly recovers the original text by walking the tree bit by bit. Beat-click Huffman coding is provably optimal among all prefix-free coding schemes. No two codes are prefixes of each other, guaranteeing unambiguous decoding. The mathematical quantity it minimizes is the average code length, the sum over all characters of frequency times code length. No other prefix-free tree achieves a lower average. Total complexity, ON log N, for the heap operations where N is the number of unique characters. Next, coin change is the canonical example for understanding when greedy succeeds and when it fails, and it's worth studying in depth. Click the greedy approach. Sort coins in descending order. Repeatedly take the largest coin that fits. For standard denominations, 1, 5, 10, 25, this always works. Try any amount up to 1,000 cents. Beat. Click but for 1, 6, 10 and amount 12. Greedy grabs the 10, leaving 2, uses 2 ones. 3 coins. The optimal is 2 6s, 2 coins. The diagram makes the failure vivid. Greedy commits to 10 in the first step, which is locally biggest, but closes off the globally better 6 plus 6 path. DP explores all options and finds the optimum. Beat. Click the DP solution builds a table where DP is the fewest coins to make amount A. Base case, DP 0 equals 0. For each amount from 1 upward, try every coin. If that coin fits, check whether DPA minus coin plus 1 beats the current best. Walk through the table for coins. 1, 6, 10. DP 6 equals 1. DP equals 1. DP 11 equals 2. DP 12 equals 2. Greedy would give 3 for amount 12. DP correctly gives 2. Beat coin underscore change underscore DP underscore trace adds a used array that records which coin was employed for each amount. Backtrack from the target amount to reconstruct the actual coins. B-click, under what conditions is greedy safe for coins? The formal criterion. For every denomination CK plus 1. The greedy solution for CK plus 1, minus 1, uses exactly CK plus 1, / CK, minus 1 copies of the next smaller denomination. United States, Eurozone, and most real-world coin systems satisfy this, which is why cashiers could always make change by grabbing the biggest coin. Irregular denominations almost never do. The is underscore greedy underscore safe function verifies this by comparing greedy and DP results exhaustively up to a maximum amount. Scheduling problems are a natural home for greedy algorithms. Here, we have n jobs, each with a processing time and a deadline. Schedule all jobs on a single machine, no idle time, to minimize the maximum lateness, where lateness is how far past a deadline a job finishes. Click the greedy insight is earliest deadline first. Sort jobs by deadline ascending and schedule them in that order. No matter how processing times vary, Committing to earlier deadlines first minimizes how badly any job overshoots. Click the Gantt chart, shows the schedule for the 6-job example. J1 through J6, sorted by deadline, are scheduled consecutively. J4, with deadline 9 but scheduled from time 6 to 10, finishes 1 unit late. Every other job finishes on time. Maximum lateness. 1. You can verify by hand that any permutation of these 6 jobs yields maximum lateness at least 1. EDF is optimal. Click. The proof again uses an exchange argument. Any schedule with an inversion, a job with a later deadline scheduled before a job with an earlier deadline, has maximum lateness, at least as large as the EDF schedule. Swapping the inverted pair never increases maximum lateness. EDF has no inversions. It's optimal. Click. The second algorithm, maximize profit with deadlines, is a different flavor. Jobs have profits, and we can only select a subset. Sort by profit descending, highest paying jobs first. For each job, scan backwards from its deadline to find the latest available time slot. This greedy ensures the most valuable jobs always get a slot, if one exists. The union find variant upgrades this to ON log n by efficiently tracking the next available slot, but the greedy criterion is identical. 2 closely related interval problems, both solved greedily. Click interval covering. Given a target range, high in a set of intervals, find the minimum number of intervals that together cover the entire range. The greedy rule. At each step, among all intervals whose left endpoint is at or before your current position, pick the one that extends farthest to the right. Then jump to that new right endpoint and repeat. Click the diagram traces the algorithm. Start at position 1. All intervals are sorted by start point. Scan forward, taking the farthest reaching interval that starts at or before position 1. That's 1, 4. Jump to 4. Now, pick the farthest reaching interval starting at or before 4. That's 3, 8. Jump to 8. Pick farthest starting at or before 8, 7, 12. Jump to 12. Continue until the entire range is covered. If at any step, no interval starts at or before the current position, there's a gap. Coverage is impossible. Click. Interval partitioning is the dual problem. Assign every interval to the fewest number of groups, so that no 2 overlapping intervals share a group. Think. Minimum conference rooms needed to hold all meetings. The greedy approach uses a minute heap of n times. For each new interval sorted by start time, if the heap's top element, the earliest ending active group, finishes before this interval starts, reuse that group. Otherwise, open a new group. Click. There's a beautiful theorem connecting the two. The minimum number of groups needed for interval partitioning exactly equals the maximum depth, the maximum number of intervals that overlap at any single point in time. The max_overlap_depth function computes this using a sweep line. Generate start events and end events, sort them, sweep through accumulating a running count, and track the maximum. The greedy interval partition algorithm achieves exactly this lower bound, proof that it's optimal. Next. A spanning tree of a connected undirected graph is a subset of edges that touches every vertex with no cycles, exactly n-1 edges for n vertices. The minimum spanning tree has the smallest possible total edge weight. Click Kruskal's algorithm is purely greedy. Sort all edges by weight. Process edges from lightest to heaviest. Add an edge to the MST if and only if it connects 2 components that aren't already connected. That is, if adding it wouldn't form a cycle. Stop when n-1 edges have been accepted. Click cycle detection is performed by the union find data structure, also called disjoint set union. Each vertex starts in its own set. Find X returns the representative of X's component using path compression, flattening the internal tree for near O1 future queries. Union XY merges 2 components using union by rank, always attaching the smaller tree under the larger. Together, these 2 optimizations give nearly O1 amortized per operation. Click the step-by-step trace, sort edges by weight. Take edge weight 1, connecting vertices 6 and 5. The 2 vertices are in separate components. Add it. Take weight 2, 3 to 5. Add. Take weight 2, 6 to 7. Add. Continue. When we reach edge 5 to 2 weight 6, vertices 5 and 2 are already in the same component. Skip it. It would close a cycle. Continue until n-1 edges are accepted. Total weight 37. Click Prim's algorithm is the alternative greedy MST approach. Grow the MST from a starting vertex, always adding the cheapest edge, crossing the cut between the MST so far and the remaining vertices. Implemented with a minute heap, it's OE log V, better than Kruskal's OE log E when the graph is dense. Both are greedy, both produce the same MST when edge weights are distinct. Sparse graphs, Kruskal. Dense graphs, Prim with a heap. Both are provably optimal via the cut property of MSTs. Dijkstra's algorithm finds the shortest path from a source vertex to every other vertex in a graph with non-negative edge weights. It's greedy in the purest sense. Always process the unvisited vertex with the smallest known tentative distance. Click the algorithm initializes all distances to infinity, except the source which starts at 0. A minute heap stores distance, vertex pairs. In each iteration, pop the minimum distance vertex. For each of its neighbors, compute the new distance via this vertex. If that's less than the previously known best, update and push the new distance onto the heap. Beat click. The step-by-step trace makes the greedy selection vivid. Start with dist, 0 equals 0. Heap, 0. Vertex underscore 0. Pop vertex 0. Relax neighbors. Vertex 1 gets tentative distance 4. Vertex 7 gets 1. Push both. Pop vertex 7. Distance 1, the minimum. Relax its neighbors. Updating distances. Pop vertex 1 at distance 4. Keep going until the heap empties. Beat click. Reconstruct underscore path backtraces from any target vertex using the predecessor map, building the actual path in reverse. This gives not just the shortest distance but the explicit route. Beat click. Bidirectional Dijkstra runs 2 simultaneous Dijkstra searches, one forward from source, one backward from destination, meeting in the middle. In practice, this roughly halves the number of vertices explored on large graphs, like road networks, giving approximately a 2 times speedup. Beat click. The comparison table is essential. Dijkstra requires non-negative weights. With negative edges, use Bellman-Ford at OVE. With a heuristic estimate to the goal, A** guides the search more efficiently. And if the graph has negative weight cycles, shortest path is undefined, no algorithm can help. Always verify your graph's weight properties before choosing a shortest path algorithm. Next, the jump game family tests greedy reachability on arrays. Each element tells you the maximum number of positions you can jump forward from that index. Jump game 1. Can you reach the last index? The greedy approach maintains a single variable farthest, the maximum index reachable from everything we've seen so far. Scan left to right. If the current index exceeds farthest, we're stuck. Return false. Otherwise update farthest to be the max of itself and I plus nums. If we complete the scan without getting stuck, return true. ON time, 01, space. Click. Jump game 2, minimum number of jumps to reach the end. The greedy insight is to think of this as implicit BFS. Each level corresponds to all positions reachable in a given number of jumps. Track, cur_end, the farthest position reachable in the current number of jumps, and farthest, the farthest reachable from anywhere within this level. When index I reaches cur_end, we must jump, increment jump count, and set cur_end to farthest. Beat the trace on 2, 3, 1, 1, 4. At index 0, boundary reached, jump, farthest is 2, set cur_end equals 2, jumps equals 1. At index 1, farthest equals 4. At index 2, boundary again, jump, cur_end equals 4, is greater than or equal to 4, jumps equals 2, done. Minimum 2 jumps. Beat, click. Why does this greedy work? At each boundary we're making the optimal decision. We've surveyed every position reachable from the current level, found the absolute farthest we can reach using one more jump, and committed to that. There's no way to do better. This is the BFS layer-by-layer argument. All variants stay ON. Next. Some greedy problems require 2 passes through the data, 1 observation per direction, before the answer becomes clear. Click gas station, end stations on a circular route. Station I provides gas, fuel, and cost to travel to the next station. Find the starting station that lets you complete the full circuit, or return -1 if impossible. Beat click. 2 greedy observations. First, if total gas is less than total cost, the circuit is impossible. Return -1 immediately. Second, simulate starting from station 0 with an empty tank. Track the running tank level. Whenever the tank goes negative at position I, we know the starting station cannot be anywhere from 0 to I, because any of those starts would also fail at or before I. So greedily set the new candidate start to I+1 and reset the tank to 0. Beat the beauty. We only need 1 pass. The final candidate is the answer. Beat candy distribution is a 2-directional constraint problem. Each child must receive at least 1 candy. A child with a higher rating than an adjacent neighbor must receive more candies than that neighbor. A single left-to-right pass handles the left neighbor constraint. If ratings greater than ratings 1, give 1 more than the left child. A single right-to-left pass handles the right neighbor constraint. If ratings greater than ratings +1, ensure more than the right child, take the max. Sum the result. Beat lemonade change is a pure greedy matching problem. Customers pay with 5, 10, or 20 bills for a 5 item. When making 15 change for a 20 bill, the greedy rule is, use a 10 plus a 5 if possible. Don't burn 3, 5 bills when a 10 serves. Preserving 5 bills is critical since they the only way to make change for 10 bills. If at any point you can't make correct change, return false. Next, a powerful pattern combining greedy with binary search to solve optimization problems where you want to minimize the maximum or maximize the minimum. Click Task Assignment. Distribute tasks among K workers to minimize the maximum total load any worker carries. Binary search on the answer, the candidate maximum load, and for each candidate use a greedy feasibility check. Scan tasks sequentially, assign to the current worker as long as adding the next task doesn't exceed the candidate load. When it would, open a new worker. If the total workers needed is at most K, this load is feasible. Click the diagram shows the pattern. Binary search maintains a range for the answer. At each midpoint, the greedy check determines whether that load is achievable with K workers. Shrink the range accordingly. The final low is the minimum possible maximum load. Click Min Machines, equivalent to interval partitioning, uses a minute heap storing the end times of active jobs. For each new job sorted by start time, if the heap's minimum end time is at or before the new job start, replace it, reuse that machine. Otherwise, push the new end time onto the heap, open a new machine. The heap size at the end is the minimum number of machines needed. Click Reorganize String. Rearrange a string so no two adjacent characters are the same. The greedy strategy is to always place the most frequent remaining character next, as long as it doesn't repeat the last character placed. A max heap by frequency drives this. Pop the two most frequent characters, append both, push back with decremented counts. If one character's frequency exceeds half the string length plus 1, no valid arrangement exists. 3 more array-based problems that each demonstrate a distinct greedy insight. Click Maximum Sum after K negations. You're allowed to flip the sign of any element exactly K times. Maximize the total sum. Greedy. Sort the array. Negate the most negative elements first. They give the largest gain. If K flips remain after all negatives are gone, and K is odd, negate the smallest positive element, minimizing the loss. Click Non-Overlapping Intervals. Minimum removals. To make a set of intervals non-overlapping, what's the fewest intervals to remove? This is the complement of activity selection. Sort by end time. Greedily keep every interval that doesn't overlap the previous kept interval. Count those kept, subtract from total. As with activity selection, sorting by end time is the correct greedy criterion. Keeping the earliest ending interval always leaves the most room. Click Largest Number from Array. Given a list of integers, arrange them to form the largest possible number. The greedy criterion isn't lexicographic, and isn't numeric order. It's a custom comparator. For any two number strings A and B, A comes first if the concatenation A plus B is lexicographically greater than B plus A. For example, 9 versus 34. 934 greater than 349, so 9 goes first. 4, 3, 30, 34, 5, 9 inches. The answer is 9,534,330. CMP underscore. To underscore key wraps this custom comparator for Python sort. Click Stock Trading with unlimited transactions. Buy and sell on any day, but you can hold only one position at a time. The greedy insight for unlimited transactions. Sum every positive day-over-day price increase. You don't actually buy and sell, you capture every upward tick. For 7, 1, 5, 3, 6, 4, gain 4 on day 2 to 3, gain 3 on day 4 to 5, total 7. Next. Greedy algorithms must be proved correct. You cannot simply test on examples and trust the result. 2 standard proof techniques cover virtually every greedy algorithm in practice. Click the exchange argument. Assume for contradiction that there exists an optimal solution OPT that differs from the greedy solution G at some step K. Show that you can transform OPT at step K to look more like G, swapping the optimal choice for the greedy choice, without worsening the objective function. If you can always make this swap, the greedy solution is at least as good as any optimal solution. We saw it with activity selection. Swap a later finishing activity for our earlier finishing greedy choice. The count remains the same. Applied to job scheduling. Swap an inverted pair. Max lateness doesn't increase. Applied to Huffman. Merge a different pair of leaves. Average code length doesn't improve. Click Greedy stays ahead. Rather than comparing to optimal, show by induction on the number of greedy steps that after each step, the greedy solution is at least as good as any other partial solution at the same step. For activity selection, after K greedy selections, the KTH selected activity finishes no later than the KTH activity in any other valid selection of K non-overlapping activities. Therefore, greedy selects at least as many activities as any competitor. Click Matroid theory provides the formal foundation. A matroid is an abstract structure with 3 axioms. The empty set is independent. Independent sets are closed undertaking subsets, and independent sets can be augmented. When your problem's feasible solution set forms a matroid, greedy is provably optimal for any weight function. MST problems correspond to graphic matroids. Scheduling problems correspond to partition matroids. Understanding these structures tells you exactly which problems admit a greedy solution. No case-by-case analysis needed. Next, understanding where greedy fails is just as important as knowing where it succeeds. Click 0/1 knapsack by ratio. Consider items with weights and values, 55, 44, 33, and capacity 7. All three have the same value-to-weight ratio of 10. Greedy breaks the tie by value, takes item 1, 50 value, 5 weight. The remaining 2 capacity can't fit either remaining item. Total, 50. DP finds items 2 plus 3, weight 4 plus 3 equals 7. Value 40 plus 30 equals 70. The greedy result is 30 units worse than optimal. The fundamental issue, 0/1 choices, aren't divisible. Greedy by ratio works perfectly for fractional knapsack and fails for binary selection. Click. Shortest path with negative edges. Dijkstra settles a vertex permanently when it's popped from the heap, assuming no future relaxation can improve it. With negative edges, that assumption breaks. In the second graph, the path 0 right pointing arrow 1, right pointing arrow 2, right pointing arrow 3 has total weight 2 plus 2 minus 10 equals minus 6, but Dijkstra settles vertex 3 with distance 5 on the first pass and never revisits it. Bellman-Ford, which is DP-based, correctly handles this by relaxing all edges v-1 times. Click. Set cover. Given a universe of elements and a collection of subsets, find the minimum number of subsets whose union covers the universe. The greedy heuristic, always pick the subset covering the most uncovered elements, gives a provably good approximation. The result is, at most, 1 plus ln times the optimal, never worse. But it's not optimal. Set cover is nitrogen monophosphide hard. No polynomial algorithm achieves exact optimality unless P equals nitrogen monophosphide. Click. The failure taxonomy. Greedy fails when no greedy choice property exists. The local best choice doesn't lead globally. It fails without optimal substructure. Previously optimal subsolutions become suboptimal after later choices. It fails on nitrogen monophosphide hard problems, where greedy only approximates. And it fails due to the horizon effect. An early cheap local choice blocks a much better global option just out of sight. Next, the practical guidelines for writing correct greedy algorithms. Click. Never assume greedy is correct without proof. The nearest neighbor TSP, always visit the closest unvisited city, can be 25% worse than optimal on pathological inputs. Just because it feels right doesn't make it correct. Always sketch the exchange argument, or greedy stays ahead proof, first. Click. Use greedy only for fractional or continuous choices. The candy and stock problems look like they might yield to simple left-to-right greedy, but candy requires 2 passes, precisely because the constraint is bidirectional. Always look for constraints in both directions. Click sort by the correct criterion. Activity selection requires sorting by end time, not start time. Sorting by start time is the intuitive mistake. It gives wrong results. Always derive the sort key from the exchange argument, not intuition. Click on the positive side. Verify the greedy choice property before coding. Validate against brute force on small inputs. Write a brute _force _validate harness that checks your greedy function against an exhaustive search on all test cases with small n. Memorize the canonical sort criteria. Activity selection sorts by end time, EDF by deadline, Huffman by frequency, fractional knapsack by ratio descending, Kruskal and Dijkstra by weight or distance. Use HEAQ whenever you need. Always process the minimum or maximum element. It's the natural greedy data structure. And combine binary search with greedy for minimize the maximum or maximize the minimum problems. Binary search on the answer, greedy to check feasibility. Next, let's put all the greedy algorithms side by side. Click the table gives the greedy criterion and time complexity for each algorithm. Activity selection, earliest end time, O(n) log n. Fractional knapsack, max value/weight ratio, O(n) log n. Huffman coding, min frequency first via heap, O(n) log n. Kruskal's MST, minimum weight edge with union find, OE log e. Dijkstra, minimum distance node via heap, O of e plus v times log versus EDF scheduling, earliest deadline, O(n) log n. Jump game, maximum reach scan, O(n). Gas station, single pass with start reset, O(n). Click the bottom section is the critical warning, 0/1, knapsack by ratio gives wrong answers. Nearest neighbor TSP is an approximation, not optimal. Greedy set cover only achieves a log n approximation guarantee. The asterisk on Dijkstra and standard coins, correct only within their required constraints, non-negative weights, and canonical denominations respectively. Click the bar chart reinforces the practical reality. Most greedy algorithms sit at O(n) log n or better. The ones on the chart range from O(n) for gas station and jump game, up to O(n) log n for the sorting-based algorithms, and OE log v for graph algorithms. Greedy algorithms are among the fastest correct approaches in algorithm design. Their strength is that single-pass or heap-driven simplicity. Beat-click. The greedy design pattern is always the same 4 steps. Define the greedy criterion, what you're optimizing locally. Sort by that criterion, or use a heap. Scan once, making the greedy choice. Prove correctness with an exchange argument, or greedy stays ahead induction. The decision tree maps any optimization problem to the right algorithmic paradigm. Click Start at the root. Does the problem have the greedy choice property and optimal substructure? If both hold, use greedy, O(n log n), or better, simple to implement. If only optimal substructure holds, use dynamic programming. If neither, backtracking or an approximation algorithm. Click once you're in the greedy branch. The problem type determines the specific algorithm. Interval-based problems. Sort by end time for activity selection and interval covering. Graph MST, Kruskal for sparse graphs, prim with heap for dense. Shortest path, Dijkstra for non-negative weights. Fractional selection, sort by value/weight ratio. Encoding/compression, Huffman with a minute heap. Scheduling, EDF for minimizing lateness, SPT for minimizing average completion time. Array reachability, scan once tracking the local maximum reach, no sorting needed. Beat-click. The greedy versus DP decision at the bottom of the cheat sheet is the rapid filter. If choices are fractional, you can take partial items, partial intervals, fractional coverage. Greedy almost certainly works. If choices are binary or integer, whole or nothing, check for overlapping subproblems. Overlapping subproblems means DP. Independent subproblems means divide and conquer. Next, the complete greedy toolkit. Click. The 4 code templates cover every pattern. Sort-based greedy. Sort items by criterion. Scan once taking feasible choices. Heap-based greedy for prim, Dijkstra, and Huffman, where you repeatedly need the minimum or maximum element. 2-pass greedy. Left to right, then right to left, for bidirectional constraints like the candy problem. Binary search, plus greedy feasibility for minimize maximum, or maximize minimum optimization. Click. The sort criteria table is worth memorizing cold. Activity selection, end time ascending. EDF scheduling, deadline ascending. Fractional knapsack, value/weight ratio descending. Huffman, frequency ascending via min heap. Kruskal, edge weight ascending. Prim, cut weight via min heap. Dijkstra, tentative distance via min heap. Coin change, coin value descending. Interval partitioning, start time with end heap. Candy, 2-pass left right. Every one of these criteria comes directly from the greedy choice property proof for that specific problem. Beat-click. The greedy versus DP decision flow. Fractional choices, right pointing arrow greedy. Binary or integer choices with overlapping subproblems, right pointing arrow DP. Binary choices with independent subproblems, right pointing arrow divide and conquer. Beat. Greedy algorithms represent one of the most elegant ideas in algorithm design. The insight that sometimes local perfection is enough. The skill is knowing when you can trust that insight, when you need to prove it, and when the problem is simply outside greedy's reach. Master that judgment, and you'll solve a huge class of problems with minimal complexity. Next. That's greedy algorithms, from the fundamental 2 properties through activity selection, fractional knapsack, Huffman coding, Dijkstra, MST, and all the classic patterns, finishing with the formal proof techniques and failure cases. All the code shown is linked in the description. If this helped, like and subscribe. The series continues with the next topic. See you there.